Neuroplasticity is the remarkable ability of the brain to change and adapt throughout life. This concept, though often mentioned, is rarely defined with precision. At its core, neuroplasticity refers to the brain's capacity to modify its structure and function in response to experiences, environmental inputs, and even injuries. During development, this plasticity is especially pronounced, shaping everything from neuron numbers to the formation of intricate connections. Adulthood, while the brain's flexibility is more limited, it still adapts through changes in synaptic strength and network organization. Neuroplasticity underpins learning, memory, and recovery from injury, but it can also contribute to neurological disorders when these changes go awry. Understanding neuroplasticity is fundamental to grasping how our brains develop, learn, and sometimes struggle. In early life, the brain is at its most adaptable. This developmental plasticity is governed by critical or sensitive periods, windows of time when the brain is especially responsive to environmental influences. During these periods, processes like neurogenesis, neuronal migration, and differentiation shape the architecture of the brain. For example, the number of neurons is fine-tuned through a balance of cell birth and programmed cell death, while neurons migrate to their destined locations, forming complex networks. Experiences such as sensory input play a crucial role. Even brief periods of normal vision can stabilize neural connections, as seen in studies with visually deprived animals. This adaptability allows the brain to recover from disruptions, but also means that deprivation or injury during these periods can have lasting effects, influencing everything from sensory processing to language acquisition. Formation and refinement of neural connections are profoundly influenced by experience. In the visual system, for instance, studies have shown that depriving animals of patterned vision during development leads to stunted growth of callosal axons and altered cortical organization. However, even a short period of normal visual experience can trigger nearly normal development, highlighting the brain's sensitivity to environmental cues. This principle extends to other sensory systems and even language learning, where early exposure is essential for acquiring complex skills. The brain's ability to reorganize itself in response to experience is not only a hallmark of healthy development, but also a mechanism for resilience in the face of injury or abnormal conditions. Yet this same plasticity can sometimes lead to maladaptive outcomes if the environmental input is abnormal or missing. While the developing brain is highly plastic, the adult brain retains a more limited but still significant capacity for change. In adults, neuroplasticity is mainly expressed through modifications in synaptic strength, how neurons communicate with each other. This underlies learning, memory, and recovery after injury. For example, after damage to certain brain areas, other regions can sometimes compensate, aided by the sprouting of new connections or the strengthening of existing ones. Island plasticity, though more restricted in humans than in rodents, also plays a role in adult adaptation, especially in acquiring new motor skills. However, the adult brain's plasticity is a double-edged sword. While it supports adaptation, it can also contribute to maladaptive changes seen in conditions like chronic pain or psychiatric disorders. Understanding these mechanisms is key to developing therapies that harness the brain's capacity for repair. Neuroplasticity is not always beneficial. While its primary evolutionary role is to help organisms adapt to their environment, the same mechanisms can sometimes lead to negative outcomes. For instance, abnormal patterns of connectivity or failed elimination of certain projections during development have been linked to disorders like autism and schizophrenia. Adults' maladaptive plasticity can contribute to chronic pain, phantom limb sensations, or the persistence of harmful habits. On the other hand, targeted interventions such as behavioral training or brain stimulation can harness neuroplasticity for recovery and rehabilitation. The challenge lies in understanding how to promote adaptive changes while minimizing maladaptive ones, a frontier that continues to inspire research in neuroscience and clinical practice.